device is it allows us to have a common wing area for the naval version as what we have with the conventional takeoff and landing version. So that vortex fence gives us commonality in terms of wing plan form for the CV and CTOL variants. That commonality in terms has major cost benefits across the services. Another good example of synergy is the multifunction control surfaces. Typically, carrier approach will drive the design requirements for the integrated flight and propulsion control system in terms of the performance of the flight control surfaces. That driving capability on the Navy version then enhances up and away performance, up and away controllability across the board for the other services. So just a few more examples of the synergistic effects. And then finally on the CTOL variant, there is some repetition here with what I showed you on the other ones, but a couple of key items I'd like to point out. First of all, the CTOL variant has the lowest cost target that's currently been defined in the JIRD. That focus on cost and affordability, as we heard in General Carlson's briefing this morning, really pays dividends across the board to all the services. It helps keep us focused on cost, making sure that we have an affordable solution that meets the service needs. Another good example I wanted to point out was the desire to minimize scar weight or minimize weight penalty for commonality. That led us to the definition of a modular concept, which I'll talk about a little more later, that allows us to meet those service unique requirements without incurring significant weight penalties or cost penalties on any of the variants. This then gives you the summary of that synergism data. These three blocks up at the top here are the three left-hand blocks that I showed you on the previous charts. As we flow those service unique and multi-service requirements through the design solution, we achieve these synergistic multi-service benefits. And if we're able to do that with a common design, there are some additional benefits, and those are indicated in red here. We bring on the capability for improved interoperability, common spares. Common spares is a tremendous driver for us to be able to reduce the logistics footprint of the vehicle and thereby, again, improve the effectiveness of JSF. It also brings about the possibilities for common training and common mission planning. Bottom line is that common design allows us to improve sortie rate and reduce logistics footprint. Now, how do we achieve that design? How do we achieve that common design? Obviously, there's a big payoff for doing that. I'd like to briefly summarize that here in what we call a carpet plot format. For those of you that haven't seen a carpet plot format before, the vertical axis is the only axis of measurement here. We're measuring increasing costs as we go up. Each of these intersections here, each of these points on this graph represent a different combination of engine size and wing area. So as we go up this way, this is engine size. As we go up in this direction, it's increasing wing area. The two primary parameters that drive the overall shape and cost of the vehicle in terms of meeting both up and away and basing mode performance. You can also see overlaid here the cost goals taken out of the JIRD. So there is a middle range of family of aircraft in terms of engine size and wing size that meets those affordability goals. Now what I'd like to do is add a few constraints here that talk about some of the parameters of interest. First of all, you see the acceleration goal. This is representative of the medium type goal that we see for the JSF. Obviously, acceleration improves going in this direction as we increase engine size. And you can see there the locus of combinations of wing area and engine size that would meet that acceleration goal. Next, we add max Mach number, again going with the idea of a supersonic STOVL airplane. In this case, max Mach is not as constraining as the acceleration goal, but tends to drive us in the same general direction. Next, we add the constraints for sustained G or sustained load factor performance, up and away maneuver capability. Generally, that parameter improves as we increase wing area, and the desired goal right now is in this part of the design space. Next, we add radius, and you can see again how that improves with additional wing area as we increase the amount of fuel on board the aircraft. That really summarizes some of the key up and away performance drivers. Now we add some of the unique STOVL basing mode requirements. You can see in purple here short takeoff capability, which again generally improves as we increase thrust to weight of the airplane. You can also see STOVL bring back or vertical landing capability, which also improves as we increase the engine size. You see here where we're starting to get a good overlap of all of these different capabilities. If you were in this part of the design space, you would be in trouble, but in this part of the design space, we have good overlap. And then finally add some of the unique CV characteristics in terms of launch wind over deck in the brown band here, and recovery wind over deck in the green band here. And again, as you look at this, you can see that there is an option for meeting all of those service unique and multi-service requirements with a common design. And that design is in this part of the design space. There is sufficient design space there for flexibility as we continue to develop the concept, but in answer to the question, can you define a common OML airplane with a common engine that meets the requirements of each of the services, we would have to say the answer to that question is yes. And not only does it meet those requirements, as indicated here, it also meets the cost goals. Now I'd like to wrap up with a few charts that talk about our innovative design solution. I showed you this graph before. What I've highlighted now is the central part. Again, in order for us to achieve these synergistic benefits, we need to come up with a design solution for JSF that has a high level of commonality. This is the Boeing JSF concept for the JSF at a top level for the preferred weapon system concept. In general, very common characteristics across the top. Common OML, outer mold line shape for the airplanes. A lot of common structure. Again, we do make use of some of the cousin part technology that Dave Wheaton mentioned. Common systems and common software on the inside of the airplane. At or above 99% common in terms of the avionics systems and subsystems on board the vehicle. The same F-119 derivative engine across the board. In our case, that's designated the SC-614 engine. We have a common chin inlet arrangement on all of the vehicles. Side-mounted weapons bays. Those weapons bays carry a combination of air-to-ground and air-to-air loadouts, again, that are in line with the current service requirements stated in the JIRD. Common control system layout with a leading-edge flap outboard, trailing-edge split flaperons, and ruddered tails. And then finally, we have a 2D pitch vectoring nozzle in the back end of the airplane. And again, that nozzle is the same on each of the service variants. So at the top level, very much commonality across the board. As we go to the STOVL variant, the unique items we add are the direct lift system components. I'll show you those briefly on a subsequent slide. For the CTOL variant, we add an internal gun. Other than that, it's basically the same as the other variants. For the CV variant, the main gear and the nose gear are unique. We add that vortex fence device that I mentioned. That device, again, allows us to have a common planform area on CV and CTOL. And again, at the bottom line, gives us a nice common family of solutions. In order to achieve that, we've defined a modular concept. As I mentioned before, this modular concept has 4 primary structural modules in the airplane. Airplane's laid out fairly uniquely in that we have this large single-piece wing structure built out of welded thermoplastic composites. That wing structure carries a lot of fuel internally. It was one solution that we found that gives us a lot of internal volume at low weight. Translates into high fuel fraction for the airplane, translates into excellent range payload for the vehicle. The mid-fuselage segment attaches underneath that wing structure, contains the engine bay and the weapons bays, basically the same for all the variants with some local tailoring to accommodate the direct lift system. You can see that local tailoring right here. Forebody component and the aft body empennage component are basically identical across the service variants. The direct lift system. You can see the propulsion system here on the right-hand side. The components in green here are basically the same across each of the service variants. We have a forward-mounted engine, followed by a spool duct section, followed by an integrated blocker augmenter section with a 2D pitch vectoring nozzle in the back end of the airplane. For the direct lift system, we add 2 direct lift nozzles aft of the engine. Those nozzles provide primary vertical lift in the STOVL mode. They rotate up inside the fuselage and stow away as we switch to wingboard mode and go back to the cruise nozzle in the back end of the airplane. We have a jet screen forward, lays out a fan of bypass air that blocks the hot gas from these direct lift nozzles from re-entering the inlet. We also, as part of our attitude control system, have roll ducting in both wings, and we have yaw nozzles and pitch nozzles in the back end of the airplane, also making up the attitude control system for vertical mode operations. And as I mentioned before, one of the reasons we selected this concept was its ability in terms of commonality potential. You see the components that we add here have a very minor effect on the overall structural layout of the vehicle, a minor effect on how we would configure the other service variants, and as a result, it gives us a real opportunity to achieve high commonality levels across the service variants. In terms of weight and reliability, it's also a very lightweight stoval system, about 600 pounds of unique stoval hardware, and we believe that is an important characteristic for this design concept in that when we're up and away, maneuvering the airplane, delivering payload, we're only carrying around an extra 600 pounds of weight that's required to do the vertical operations. And then finally, this concept again allows us to have a common engine across each of the service variants, and in working with Pratt, we've been able to define an engine that does the job for us in vertical mode and is also an excellent engine in terms of performance for supersonic capability, maneuver capability, and SFC required for good range capability. And then in terms of how the airplane stacks up for basing modes, as we said before, a lot of these service unique requirements are associated with different basing modes. With the compact common design we've defined, we do an excellent job of meeting the different basing requirements. On the CV big decks, we do not require a wing fold on the airplane. We have a spot factor of less than 1. Without that wing fold, we can position 2 aircraft side by side on each elevator, as well as 6 in the 6-pack without that folded wing. In terms of the Marines airplane, fully compatible with both LHD and LHA performance requirements. We can also, again, spot this airplane on the stern elevator on the LHA without a wing fold. And then finally, for the UK Royal Navy airplane, that airplane is the same airplane as what we envisioned for the US Marine Corps. That will spot on the same spot lines as the Sea Harrier. Will also fit the centerline elevator on the Invincible class ships without a wing fold. So to summarize my comments, I guess this is the bottom line for what we've seen to date in the JSF program. In terms of requirements development and requirement synergy, there's really what I would call a sweet spot here in terms of affordability and capability. And JSF requirements have really zeroed in on this area to give us an airplane that's both capable and affordable. And when we translate that into effectiveness of the weapon system, there are also knees in the curve there, as I mentioned, in terms of cost versus effectiveness and performance versus effectiveness. And so this combination of affordability and capability also gives us a very effective weapon system. That concludes my presentation. I believe we'll be taking questions a little later. Okay, thank you.
Let people get rewired here for a minute. Dennis, thank you very much for your remarks. I have to tell you that was a very excellent explanation of how we do cost and performance trades, which really are the key to the affordability of this airplane. And these cost and performance trades are being performed with industry, the program office technologists, and with our warfighters in concert with each other. So everyone is accountable for the cost and affordability of this aircraft. And I believe that's what's going to make it a success in this area. Our third and final speaker today is Mr. Frank Gillette, who's also an engineer and currently Director of Advanced Military Programs in Pratt & Whitney's Government Engines and Space Propulsion Division. He's been with Pratt since 1962, and as such, as a mechanical designer, has worked jet and rocket engines for all those years and progressed through increasingly more important positions. He's worked 15 years of his career on the F-119 engine, which currently powers the F-22 aircraft. He was honored by the American Institute of Aeronautics and Astronautics in 1991 as National Engineer of the Year. He was the Aviation Week 1991 Laurels Award recipient for developing the thrust-vectoring supercruise engine that does power the F-22. And he received the Society of Automotive Engineers prestigious Cliff Garrett Turbo Machinery Engineering Award in 1994. I think his achievements speak for themselves, And it's needless to say, we have a real opportunity today to hear from an expert, a true expert in the field of aircraft propulsion systems. Mr. Gillette.
Can you all hear me? Good. Thank you, General Kenny. I can hardly wait to hear what I'm going to say now. Let's see if I can find that laser light. Got one? Yeah, good. Now you've heard all about the airplanes and how easy they are. Let me tell you, our admiral's got us targeted right where we should be. I like to be number one in football, but he's got us number one with the most concerns, and he's right on target. This is a challenge. I wish our engines were transparent to this whole system, but they're not. And as I go through, you're going to see that it is a complicated system. It's the most challenging I've ever worked on, but it's going to be exciting when we see these airplanes fly out at Edwards and then we get them over to Pax River. We are working on the essential requirements of the program. We're working hard as a team, and this is the first time in my career where we really had a team. We're either going to team and have a marriage, or we're not going to make it work. We're working with the airframers. We got a lot of different engine people we're working with, and probably our biggest challenge is how we're going to do our software. So it's going to take a lot of talking, and we really have to work as a team. I'll go through some of these later on, but it is exciting to do this and integrate engines within an airplane to make this work. This is our essential elements that you've heard the other two speakers talk about. Affordability is going to be number one. If we don't make this affordable, Congress isn't going to buy it. And I think this is our biggest challenge that we have to work on. And of course, we do that with the commonality of the core with the 119 and going through a lot of lean enterprise. And I don't think we do enough of that. We've got to keep working that and doing value engineering and new ways of acquisition. As far as the next is, of course, survivability. We have to have, for our grandkids, the first day strike. And we can't wait for just one airplane to do this or two. And I think we've got the capability, we've got the technology, we've got to do it affordable, but we can make survivability, have a low radar cross-section. We can increase maneuverability by what we have. In fact, I'm kind of exciting. I think our spool-up times are even going to be better on this engine we have in the 119 because we did add some turbine to it. And so we'll have great maneuverability. The big question is single-engine safety. That's got to be primary. I think our objectives have to be first to pilot, always to pilot. We can always buy hardware, then next to hardware. So we really have to work at that, and we're doing that through a redundancy of a lot of the components on the engine. The next one, of course, is supportability. I think the way our grandkids will win the next war, if we have that, hope we don't, will be in supportability. I'll talk a little more about that, but I've got a great passion for that. We need diagnostics, which you can see there. With single engines, we have got to determine when it's safe. Obviously, the only worry I have with diagnostics, I hope the pilot never shuts the engine down until it shuts itself down, and he does that. Bring it home. We've got a lot of multi-service commonalities. This is a unique thing. I'll show you a little bit on the slides how we can do that to really cut down on support. And then, of course, the equipment will be the same. Lethality, we have got to have operability. There's no pilot that wants to give an engine a roll aid if it burps. And we've got to make that work, and we can do that. And of course, we do have thrust vectoring. I'll be going through a little different, excuse me, than what we did in the program. I always go alphabetically, and then I don't get in trouble. Sometimes I have trouble with my ABCs, though. But we'll start with Boeing. You just saw some of this. This is the lift concept. We've talked about the screen that's right in here. The screen is a bunch of air that's coming off the ducts, in which will not let the main propulsive lift force have any of that air come back through the inlet, which would cause stalls or lose performance. Those parts are being made by Rolls-Royce right there. And then, of course, this ductwork down through here is being made by Rolls-Royce. We do have an integrated remote nozzle for augmenter. This will be the first time we've had a Stovall-type aircraft with an augmenter, so we can get our piece of best and we can get away. And, of course, we have an integrated 2D CD nozzle, which is basically like we have in the F-22 right now. The fan is a scaled fan from the F-119. It is bigger. And in the back right here, we have put an extra stage in the low turbine, which we have scaled up to drive that big fan. By having that extra stage, we spool up very quick, and we do have the energy so that we will have good thrust response to pilot alike. Now, when we're in the VTOL mode and when we're in the CV mode, these components, of course, just aren't there. So it's essentially a common engine, and we remove these components, and you saw a few little pipes that come out the back. So we got a very common engine in all three of the variants. This is the Lockheed shaft-driven lift fan concept. Let me just start with the engine first right here. We have an increased fan size from the F-119. We've scaled that up. We did add another stage in the turbine to drive that, and also to drive the shaft, to drive the clutch here, and of course drive this engine. I should say fan. If you look at the mock-up out here, really Dave's got a super mock-up. This is a counter-rotating fan that's being developed and designed by Allison Rolls-Royce, and that's coming along good. And then there's a nozzle here which they use for directing the thrust. Then we have on our ducts, we've got openings in which we have the roll control right here, and that's also being designed by Rolls-Royce. Coming along really well. I'm very appreciative of what Rolls-Royce has done this time, a lot better improvement than what we had in our LSPM, and they're really coming up. And of course, this will stick in the wings, and there's a lot of integration, and that's working well. Then we have the three swiveled, bearing swiveled ducts right here, which lets the force come down vertically. And Rolls-Royce is doing that. They've done a lot of work with in the UK on that, and they've got more experience than we have. We designed one back in 1976, and it kind of went away when we went away from doing the VTOLs. But they're doing a good job. That's working well. And of course, then we add a nozzle right here. So that's how we are in the Stovall mode. Then when we get into the conventional mode, we just take this engine right here, and we have a conventional axis nozzle, and it's coming right along real well. And I'm proud of the effort so far and where we are this part of the program. I'll talk about that as we go on. We have started with the 119 core. That'll give us the most low risk. The core has got, counting the prototype and what we have now, is about 7,000 hours, and we've learned a lot about that core. We've changed a lot, and that gives us a real fundamental base to start with. And then we have a fan on both engines that we've scaled, and I'll have to tell you, made the aerodynamics better than what we got in the 119. We know where we've gone awry in some of the spots. That will be changed in the 119 when they get in the ISR, so we've improved the fan a little bit where we have some separation. They're going to have better performance. We want to use common materials. That helps us in process. It's going to help us in cost and works quite well. Gearbox and lube is going to be the same as what we had in the 119. Controls, we use the same controls we had in the 119. The 119 controls are redundant. The actuators have redundant power. They have redundant hydraulics. The only thing that isn't redundant on the engine is where you have an actuator, and that's the push rod. Everything's there except the push rod. So we've got 6 actuators, and then the tower shaft in which you take the load off the core that drives the gearbox. That's single. Now, we have watched what other people have done to try to make that redundant, like basically Tamansky over in Russia. It just cost too much and reliability went down. So that's the only thing we don't have that isn't redundant. We have 2 pumps on there. The engine will come back with 1 pump. You just can't use the afterburner, but it'll bring them home. The external architecture will keep fundamentally the same as what we have in the 119, except we want to do the maintenance a little faster. And then the turbo machinery, which is from the fan all the way over to the turbine, is the same on all variants. In other words, the Lockheed variant has the same, and so does the Boeing variant. We really got to work on affordability. I think this is still the challenge. If we don't get the cost down, Congress is just not going to buy what we need or buy it at all. So we start with a lot of commonality. We want to use the same type of hardware, the same type of processes. If it's scaled, we use the same machine so we can cut down on the times, use the same knowledge. We want to use the same materials, same processes, and same support equipment. Very important. This support equipment will be out there. The Air Force is going to pay for it, and there's no reason why not to use the same equipment here. And then, of course, we've gone through the fundamental things that every company's done on the lean enterprise. We have a great technology maturation program that Admiral Steidel has initiated. We didn't have that in the 119 program to work on cost, and I think that's where we should put our money so that we go in EMD, we will have a lean and mean engine. We've really been working with the suppliers, and I'm very proud of how our suppliers have worked on their cost. 70% of the engine's going to be from suppliers, and they've got to be teammates. They've got to be married to us. We've got to be married to them just like we do our wives. And sometimes we might even be working better with them than we do our wives. We at least see them more often. Diagnostics, we've got to do something for health. Flying off an aircraft carrier, the water's kind of cold out there, and we do need a good diagnostic system that is proactive. We have systems that can tell you something failed. That's pretty easy to look at it. But we need to be proactive, and we're working that. I'll talk about that in a little bit. What's going to make or break this program in single engine is its safety. You can see where the current Harriers are here, and that's not a criticism, that's just fact of life. You can see where we are with the F-16. Up here at the top, we're with F-16s with the F-100, 200. Down here, we are with the 220. Knock on wood, we haven't had any problems with the 229, and of course, we don't have any data yet, and I hope we never get it for the sake of the pilots. We have got to be over here. We've got to be under 1. It's doable if we focus on that and make sure reliability is number 1 for the pilot. If you go back through the history, we started out in the early 70s with the F-100 and the F-15. We had about 250,000 hours. Then we went in the F-16. We went in F-16. We had to put a backup buck on there for pump and so on. And we don't have to do that now. It's already there. We've learned that lesson. We've designed the 119 with single engine mentality. Now we're coming along with the F-22. When this program, if it stays on schedule, goes into EMD, the F-22 should have about 700,000 hours. So this engine, when it goes into service, is going to have approximately 3 times as many hours we had in the F-16 when we come to the single engine Joint Strike Fighter. So that'll get a lot of lessons learned, and what we really got to be sharp on is lessons learned. A lot of times people don't like to mess in that area, but this is going to be one of the most critical factors to follow through this program as lessons learned on the F-22. Diagnostics, our Admiral is really on target. They banged us pretty hard because we weren't working diagnostics as hard as we should be, and he's right. And so what we've got here is a lot of ideas on diagnostics. We've got some acoustics that we've been trying on engines to see if we can detect any type of failure. Our basic failure that we worry about is high cycle fatigue. We do design the blades for being damage tolerant. We do design the blades such that we have vibratory thresholds so we can stand a certain type of crack. But that is the basic problem we have on all the jets now, and that's with everybody. So we've got some other ideas we're working to try to do that. Electrostatic monitoring, when we're running an engine, if you're on a deck, you could run it and see what's coming out of the back, and if there's anything metallic or anything like that, we can pick it up. I get worried now that we're going to rags and glue, or I should say composites, they won't show up, so worried about that. But on the metal parts, your turbine parts, that'll pick that up, and it's very good. Fall detection, isolation, that's going to almost be a no-brainer when this engine flies. We've demonstrated that quite well on the F-119, and that's really exciting, so that if you really wanted to, and I don't want to put an overload on a pilot, and I don't think we should, but a pilot could really look on his Atari set there and his oscilloscope and tell what had to be changed out. You could come in, you could change out a component at the same time you're putting on, loading up the weapons, because every one of these components can come off and on with CBR gear on in 20 minutes. So you can actually do that. In fact, I think the commercial guys should start doing this so I'm not late to come to meetings. We've talked about this in the other programs. A good way to do logistics. With all the computing power we have, there's no reason we can't track all the part numbers, all the lives of every fracture critical part, so that the maintenance people know what to do, when to do it, and how to do it. Oil conditioning. We've got that on the engine. We can tell what the oil is. Instead of looking at chip detectors, we can look at that automatically. We haven't taken the chip detectors off because people are still old-fashioned, but we have them on there as a redundancy, but we can tell how the oil is. There's algorithms for health. We can monitor the engine on health all the time to know where the deterioration is, as far as if we're losing abradables, so that the pilot knows where he is and when we should bring it back, when we should not send him off. We've got automatically storm, which is just self-tuning on board a real model to keep the thrust up. We want to send the pilot out knowing what he's got for thrust. We don't want to have it trimmed. It can do all that itself. And of course, we have the full authority digital electronic control, which is redundant. We've got 2 of them with 2 computers on each side, which can challenge each other with algorithms to know how the airplane's running. We got a new thing with eddy currents. We're trying to do that. This hasn't been perfected. I don't want you to go away thinking this is a done deal, but it's something we're doing in our technology maturation program to see if we can understand how the blade vibration. It'll tell you flutter. We haven't really figured out how to get it to do integral order, but we can do non-integral order, and we can tell if something's going on. Now, we have to figure out what stage to put it. We can't cost a lot, and it can't cost a lot of weight, and it can't hurt us on maintenance, but our Admiral's really hitting us hard to work on maintenance, and for a single engine, that's what we should be doing. Now, this is part I get kind of excited about. I've been all over the world. I've worked on every engine. So I've worked with Phil Combs and Griswold on their engines. They've worked on ours to see what we've really done. And about 15 years ago, I went out in the field, and I was convinced our product lines were tools, and we sold them engines to use our tools. And right now, and we don't have to do that. We didn't think about tools up front. In the 119 program, I challenged the whole team to 6 tools. And you check how many you got in your car, you take your family. You don't have too many, but you got to have enough to get basic things done. We started with 6, and we ended up with, or started with 5, we ended up with 6. And I will tell you, you can take every LRU off with those 6. Now, I don't want to tell you that's all you have to buy. I want you to use the standard toolkit. I want you to use speed wrenches. I want you to do it fast. But if you get the mindset that you can use 6 tools, and I can take them off as a shade tree mechanic with a CBR gear, and that's a test I gave everybody, and it's got to be fun down there, and I enjoyed it. And I will say they all work with 2. It gets a mindset, and we have got to work supportability. I'm convinced, as I've ever been, that support will be what wins the next war. And if you watch how those Marines work, which I really admire, and after being in the Navy, they work out of a box. Everything's in a box. They're ready to go. Then you go on the aircraft carriers, and that's a little bit tougher. And of course, the Air Force has got the easiest job. Now, when we started this, when the 119, I had Captain North. Some of y'all might have known him, worked down at NavAir, and only reason I know him, he's a Gator, and so kind of Gators stick together. And I had him bring a lot of people down. So I won't take credit for the externals of these engines, and Pratt Whitney should take credit. It was really a lot of workers. We had over 300 people come down and tell us what they needed. Engineers know how to do heat transfer and do stress analysis and that. The mechanic knows what he wants. And so we made a lot of changes just from what the mechanic, and I could go through a litany of things. We don't have the time, but it's exciting. And we're still not there. We got to do better. But if you take where we are in support equipment right there, F-100, it's got 650 tools. The 119 came down there, and we went down to 197. Right now, we're pushing at 175, and Admiral Steidl challenged, why do we have that much? Let's go down by 30%, and I'm totally agreeable. We've got to get that down. You don't need all these tools. There's ways of doing a lot better. C-141s, right there for just the engines on the F-100 is 1.6 C-141s to take engine parts along. So that'd be like your car. If you had your car and you went on a trip, you take 2 trailers to repair the tires. It doesn't make kind of sense for an automobile, and doesn't either for the Air Force or Navy or anybody else. We've got it down right there to 6.2 with the 119. I won't tell you what this number is because it's really competitive between the two gentlemen who have been talking. But I'll tell you it's down in the tenths, and it's got to go down. We need to haul fuel, and we need to haul ammunition. We don't need to haul tools. That's not what we fight with. We fight with ammunition, and we fight with fuel. So we got to get this down so we can carry the real parts. And of course, the support cost has come down significantly because of simplification of the tools. On a single-engine airplane, or even any airplane, in fact, the commercial guys, the main thing we want to do is give the pilot the freedom of the throttle. I wish our engines were always transparent, and our engines worked in airplanes like my wife expects an engine to work in a car. Turn it on and never worry about it. She doesn't even pay attention to gauges unless a light comes on. And then she doesn't know what that means, and she calls me. We need to have these engines so the pilot can look up the heads up or look through a scope and go kill the enemy. And so we got to have rapid throttle transients, and that's doable with both of these. And you're going to be surprised how fast they're going to go. No restrictions. Let them do what he wants. Let them come up. Let them go down. Stall free. Reliable ground start and air starts. And I'm talking air starts 30,000 feet in a good envelope. And then, of course, if anything happens and something goes down, we automatically restart. It usually takes you about, on anybody's engines, 30 seconds to restart. Well, we need to have that, and we got enough brains on this thing that we can go auto start. The pilot can auto start it, or it can auto start itself. But I think we should auto start such that we're ahead of the pilot. He can't do it as fast as electronics we have, or she, and that's what we need to do, and we can make this work a lot better. This is where we are with our milestones. We have a monthly meeting. The JPO office is very good to come down and go through this for 2 days every month, and we're there. We've got the contract. We completed and I'll tell you a little more about this, the AMT for flight clearance on the 119, and we're get to go. We've had our kickoff, very good meeting. We've had executive reviews. We are cutting chips. This is a real program. This is the exciting part. Paperwork is kind of neat, but boy, when you see the chips, you get kind of pumped up. We've gone through a design review. I'll talk about that. Maintainers in loop. We've had one of those meetings. We've got to have a little more. We missed this last month. We only got about another 2 months to make that happen, to make an impact on this first go-around. And I'm working with the Marine Colonel, and we're going to make that happen. And, of course, the controls, we're integrating the controls and starting that testing. This is the first blades off the 119 after we have passed 1,021 cycles on the AMT. I'm very pleased on how these blades look. We will be running a little bit hotter than the 119. The 119 did have some, they did run 50 degrees hotter to demonstrate it. But if you take these blades, put them on our CDA mission, which we got to go fly, we're A-OK. And that's a good starting place. Now, when we get an EMD, we will change these blades. So I don't want you all going thinking these blades are all done for life. We'll go in and put some more supercooling so that we get the full life. These blades are really good. Won't have any trouble in a CDA, but they wouldn't make the Marine life that we want to give the Marines in the end of the program EMD. So we'll change these blades to supercooling. But I'm very proud of how this turbine's worked, and the 119 is cleared, and we're ready to fly. Put this in so you see, this is the intermediate case. The core is the same. We had to change intermediate case because we have a bigger fan. And that's the two intermediate cases. And you can do a lot of stuff that people think you can't. The JPO office and us went for our first trip out to PCC, Oregon, and we had a sit down with Bill McCormick, the CEO, and the dates on these cases were December of this year. Now, if we want to go to test in April of next year, and we'd like to move that up 2 months, you can't receive your casting in December. Went out there with an open mind. We made a few design changes that they concurred with. The cases are poured. We'll have finished parts on my wedding anniversary, which is June 9th, so I can remember that date. But there's both cases. We're coming along. So this program is real, y'all. It's not talking about all the studies that are going on for preferred weapon system contract. We are making hardware. We're going to go fly, and this is what's exciting. When you see the hardware and it starts going on the floor. Now, we expect all the hardware to be on the floor in October of this year so that we can get to test 2 months ahead of schedule. This is just a quote that Colonel Mayoko said. He ran a design review, and boy, it was a hectic week. We had meetings going on everywhere. I felt good about the preliminary design. We were actually we're ahead of what the expectations were. And some of that is because of our tools have changed since when we did the 119. We've got CFD, and we did a lot of stuff like that, and we're a long ways off. And I was very proud of the team. They did good. Bob C. is our program manager, well organized. We had about 180 reviewers. It was a good test, just like going through the orals all over again. But we're on our way, and this is a good sign. Now, we got to keep it going. We will have our CDR October, and that's kind of right at the same time hardware is. So the Admiral's crew can challenge us. We can go down the floor and look at the hardware as we go through the review. But we're coming along. This is a real program, and it's our responsibility to make this program happen so that we do go fly. This is a supportability review we had down at Pax River, which we had all 3 of the services down there. We brought the 119 mock-up down there. And the way you do a good review is let the mechanics work on it. These are Marines right here. You can see that they've got a speed wrench right in his hand. John Grohowski there is the chief designer for the externals. But we let everybody take these things off and on. And this is where you learn. This is where you get the ideas. And we need to improve even what we got in the 119. But you can take all the line replaceable items like a FADEC on and off in 20 minutes. And I don't know if we're going to get that time down more, but we can at least get the equipment where it is easier and more accessible on the airplane, on the main deck, or for the Marines. This is our schedule, the only schedule I have on there, but I think it's important that everybody understands where we are, where we're going. This is where we are right here. So we talk about the end of April. We're really calling about 1st of May. We've had our preliminary design. We're working on flight clearance. We're heading for first engine to test in April. That's on our schedule. We'd really like to go 2 months ahead of time. You never have enough time to test, analyze, and fix. And in our business, if anybody thinks they can do it perfect, they can't. I don't know how many of y'all got hundreds all the way through your engineering schools, but maybe you did. I wasn't quite that good, but I had pretty good grades, but didn't get 100 every time. So you're going to have a phase of test, analyze, and fix. So the quicker we get there, the quicker we'll be ready to first flight. And boy, what a way to go into the next millennium, but to fly 6 variants. I mean, this is going to be an exciting day for our country. We can make this aircraft cost what it is and what the Admiral's pushing for and what we need. This is going to be a great day for our country. And none of us, well, some of you all will. I won't see it. I'll be in a box, but I'm going to look down, and these guys screwed up. I'm going to trip you. I can't talk to you, but I'm going to trip you. You just watch. And this is great. This is for our grandkids. This is for what's going to be exciting. They're going to fly it as Dave talked. I like that little kid in the helmet. We really got some that are still gleams in Daddy's eyes. Come along here, we're talking about the preferred weapon system contract. We're working that real hard. You saw all the different trade studies. We got to do that. This is what really counts down here. This is what the pilot's going to fly. This is what we're going to demonstrate to show this technology is real, that we can do it, And down here, we've got to execute what we learned up here, down here, and make sure the cost and everything. And I'll tell you one thing I didn't put up there in the pillars. Biggest challenge the engine has, just so you understand, is not only the complication of all the integration and everything, is weight. Weight is very critical when you're talking about the Stovall application. And I don't want to put that under the table. I want you to know we're struggling with that, and that's a reality. And it was a reality on the Harrier, and it's a reality today. So that's one thing. And that's what we're working with a lot of ideas how to get this down and get the right weight. Technology maturation. Been in the business 36 years, and it seems like every time we have a new program, somebody has a better idea than the next one, thank goodness. We needed that in the 119 and the F-22. The Admiral has set aside quite a bit of money for us, and we're talking like $90 million to start working on cost, working on diagnostics, and be ready to go in full scale here. And if there's any problems that the airplane has today in the F-22 and the engine, is the new technology that we didn't do. And shame on us if we're not ready for what the Admiral has provided for us right there. And we should not have some of those new technologies where it costs a little extra money. We've stumbled a little bit. We've made them work and struggled in the F-22, F-119. So this is a great plan, and we're working that hard. And we'll actually go put this into an engine. The F-22, 119 folks are going to give us an engine. We're going to put all this stuff in an engine and test it before we have to write the proposal. So the onus is on us that we prove it out. Now, when you write a proposal, it's a lot easier to talk it in words than it is to show the facts. So the Admiral's got us to show the facts down here, so we have to put our money where our mouth is. We're committed to this program. I think it's exciting. I think the team's working really well. It is very complicated, you all. I don't want to undersell that. We're working together. I hope that what we do as a company at Pratt & Whitney, we're transparent to both Boeing and Lockheed. We need to go out there and make the best airplane for our country. I realize there is competition, and that's good. Phil Combs is a good buddy of mine. We've worked together, fought together, and I guess we've been competitors together. We understand that. That's okay. That's what we need to make this country strong, and that's going on. And all I want to tell you is we're ready for the first engine to test. We want to be there, and we're proud to be part of this team. And I hope we come across humble that we got selected on both of these, because if we do anything that starts with an A, I get upset, the word that starts with an A. And I hope we fulfill our commitment, not only to the JPO, but both weapon system contractors. Thank you very much.
Thank you, Mr. Gillette, and thank you for really emphasizing the supportability part, because that's another area that we believe we can make a giant reduction in cost of ownership of this large fleet of aircraft. And each of our prime contractors have an emphasis in that area, I'm happy to say. We do have time for questions that we can go into now. I'd just like to acknowledge that this leadership that you see here represented by our industry panel is leadership that's on a fast train. We are have had some initial design reviews this year. We will have all the initial design reviews for propulsion and both airframes this year, critical design reviews next year, start building airplanes, roll them out in 99 and fly them in 2000. And that's pretty fast, but this team, all these teams that are represented here are up to it, and the program is going extremely well, and it's on schedule right now, so we're very happy about that. I guess we can go for some questions if anyone has any. Well, I can't see a thing. Yeah, unless there's somebody out there identifying someone for questions, you can't see anything up here because of the lights in the back. Harris, are you back there? Any questions?
Questions?
Nope. problem. We just appreciate your attendance and thank the American Helicopter Society for their focus and interest in the Joint Strike Fighter. Thank you.
Should have figured out a better way to do this. It was